Hello, this video is going to be covering the photoelectric effect. So what is the photoelectric effect? Well, the photoelectric effect is when photons or light hits a material and then electrons are ejected off. So when you have a material such as metal here, so I'll draw it up really simplified. When you have some material here, um, they say this is metal. This has electrons floating inside of it. So there's going to be a bunch of electrons in here. Now, when light shines on it, so let's just say you have an incoming photon here. When light hits this material, so this light has a certain energy, but this photon here has a certain energy associated with it. And now this single photon can hit a single electron and cause the electron to eject off. So the electron would then get ejected off here and it would have the same energy, E, because conservation of energy. And now this electron would be called a photoelectron. So this is a photoelectron. And so a photoelectron is just what it's called when an electron gets ejected from a material because of an incident photon. Now, um, if we look at experimentally found like results here, we see that for a given intensity of light, so for a given intensity, so if you shine light on, so if you shine a beam of like a flashlight or something onto this material here, for a given intensity of this light, if you graph the number of ejected electrons against the frequency of the instant light, so if you could change the frequency of it, so this is the number of ejected electrons, so electrons, and then this is the frequency. You'll see that below a certain frequency, there's going to be no electrons that are ejected. So it's zero. And then at a certain frequency, all of a sudden electrons start getting ejected from the material. And then you see that the number of electrons ejected for a given intensity remains constant. And then this frequency here is called the cutoff frequency, so FC. Um, Now, what does this mean? Well, if we look here, um, we'll see that once light reaches a certain frequency, so the energy of a photon is associated with, or is directly related to its frequency. So once light reaches a certain frequency, meaning that it reaches a certain energy, it's able to start ejecting these electrons and creating photoelectrons. However, increasing the frequency beyond that cutoff frequency doesn't increase the number of electrons that are ejected. So this points to light being quantized. So what this means is that light is quantized into discrete packets of energy. So increasing the intensity increases the energy of all of the instant light. So if you have a higher intensity, or sorry, increasing the frequency increases the energy of these incident photons, but it doesn't increase the number of electrons that are ejected, meaning that the energy of these ejected electrons also has to increase. But what this means is that light is quantized into discrete packets. So into discrete packets of energy. And then these are called photons. So when you increase the frequency of light, the energy of a photon of light increases, but the number of photons doesn't change. So that means that the number of ejected electrons won't increase when you increase the frequency, even though the energy of the incident photons increases. The number of these ejected electrons stays the same because the number of photons coming in depends on the frequency, not on the, depends on the intensity, not on the frequency. So if the intensity stays the same, then the number of photons stays the same, which means that the number of electrons ejected also remains the same. And that can be seen on this graph. And so if you change intensities, so like if you had a higher intensity of incoming light, that would mean that there's more photons, but the cutoff frequency doesn't change because, so this is higher intensity. The cutoff frequency doesn't change because the number of photons changes, but the energy per photon doesn't change. So the energy for a particular photon depends only on its frequency, but the total energy of all the photons depends on frequency and intensity. And the number of photons only depends on intensity. So if you have higher intensity, then more electrons can get ejected and there'll be more photons, but the energy per photon stays the same, which means that the cutoff frequency also stays the same. And a lower intensity would just look the same as well, but the line here would be lower and constant. Okay, now if we look at a graph of the energy of the photon, of energy of the electron that's ejected, and against the frequency of the incident photon. So if we graph, this is the kinetic energy of the photoelectron. And then this here will be the frequency of incident photon. So this is the frequency or the color, you can think of it, of the photon that's coming in of incident photon. We'll see that so there's no electrons ejected below the cutoff frequency. So if we put the cutoff frequency here, we'll see that electrons start getting ejected at the cutoff frequency. And then if you do this experimentally, you'll find that the energy of the photoelectron increases linearly with the frequency of the photon. And so the energy of this photoelectron is directly, or it's linearly related to the frequency of the photon, which means that the frequency of the photon should be directly related to the energy of the photon, which is what we already established. And now this slope here, the slope of this line is called, so is equal to h, and h is Planck's constant, and I'll cover that in a bit. So now if we extend this line backwards, we'll get a y-intercept, and this y-intercept we can call phi here, and this is the work function. And so if we think of this blue line as indicating the energy of the electron, then we see that once, so as frequency increases, that means that the energy of the photon increases, and then the photon imparts all of its energy into the electron. And so the electron starts out with negative energy. And when it has a negative energy, that's potential energy, really. So in this region, you really should think of this part as potential energy. So this is potential energy. And then so this means that it's bound. So when this energy is negative, so and when energy is negative, that means that the electron is bound to orbit something. So it's, in this case, it's bound to the nucleus of the atoms of the material. But then as you start increasing this, as you start increasing the energy of the incident photon by increasing the frequency of it, potential energy decreases, and so this is the total energy. Potential energy decreases and kinetic energy increases. And so really, I'll say that this is, I'll put this as, relabel this. So this is total energy, including potential energy. Okay, so as the energy of this incident photon increases, the electron absorbs that energy, and so this total energy becomes less and less negative as the incident photon increases energy. And once it breaks zero, and once it goes positive, that means that the electron is no longer bound to an atom. And so since total energy is positive, that means that it can have zero potential energy and have kinetic energy still. So that means that the electron gets ejected from this from the material here, and then that's where you start seeing that it has this it becomes a photoelectron, and then it gets ejected off with a certain energy um, given by this function here. And really, I should say that um, the incident photon has an energy E, and this electron will have an energy E minus the work function here. So total energy is still conserved, but some of the energy um, from this photon here is put into removing the electron from the material. So it some of the energy of the photon overcomes the potential energy of the negative potential energy of this electron that allows it to be ejected. And so if we write out the equation for this, we get that K, so we have K max is equal to HF minus phi. So K max here is equal to the maximum kinetic energy of a single photoelectron. So that's the maximum energy that the photoelectron can have after being ejected from this material by an instant photon. And this only makes sense when this frequency is above the cutoff frequency, because kinetic energy has to be positive or zero. So this equation here doesn't really make sense when or like this form of it doesn't make sense when this frequency is below the cutoff frequency. So when it's below the cutoff frequency, you get that the total energy of the electron is going to be equal to this, and it's negative, which means it's still bound. But when the cutoff frequency, when the frequency is greater than the cutoff frequency, then this equation gives the maximum kinetic energy of that electron, of the photoelectron. Now, if we look at this HF term here, so this HF term, this is the linear part of the this function where this increases as f increases. HF is equal to the energy of the incident photon. So the energy of a photon is given by E is equal to HF, where H, or F, is frequency, and then H here is equal to Planck's constant. And Planck's constant is just the proportionality constant between the frequency of a photon and its energy. And so H here, H, Planck's constant, is equal to 6.626 times 10 to the negative 34, and this is an approximation. It has much more much more digits than this. Joules per second, well, not joules per seconds, joules times seconds. And it is also equal to 4.136 times 10 to the negative 15 electron volts times seconds. Now an electron volt, so an electron volt, denoted EV, is a unit of energy. So this is energy. And then an electron volt, so it's like joule, so it's a unit of energy, but it's different from the joule. It's much smaller. It's defined as the work required. 1 electron volt is defined as the work required to increase the electrical potential of an electron, of 1 electron, by 1 volt. Okay, now if you remember that electrical potential voltage is equal to energy divided by charge here. And so energy, which is our unit, is equal to charge times voltage. And now the charge of an electron is equal to E, which is the elementary charge, or it's really equal to negative E. But so the magnitude of the charge in an electron is going to be equal to magnitude of the charge in an electron is equal to E, which is equal to 1.602 times 10 to the negative 19 coulombs. So this is the magnitude of the charge in an electron. So to increase the electrical potential of an electron by 1 volt, we need to, this is equal to E. So you can think of like the symbol for an electron volt is EV, and then you can kind of calculate EV by multiplying the elementary charge by V. And so this just gives 1.602 times 10 to the negative 19 times 1 volt, and that's equal to 1.602 times 10 to the negative 19 joules. So 1 EV is equal to 1.602 times 10 to the negative 19 joules. And you notice that this number is the same magnitude as the elementary charge. So that's just 1 electron volt. And so that's another way to define Planck's constant. And now finally in this equation here, we have phi here, the work function, which we see on the graph is the y-intercept. And we're subtracting this, so it's really the negative of the y-intercept. So this phi, so this is the work function. And then this is equal to the work required to remove an electron from a material. So this is the work required to remove an electron from a material. You can also think of that as like the potential energy, or like the magnitude of the potential energy of the electron, because you need to overcome that the potential energy in order to eject the electron. And so that is the work function there. So this equation up here is how you can calculate the maximum kinetic energy of a photoelectron given the frequency of an incident photon and the work function of the material. And for different materials, you'll have different, the slope always remains the same, which is Planck's constant. But for different materials, you can have different intercepts. So like for a different material here, we could have a line that looks like this, where this is like, if we call this like metal A, and we call this metal B, notice that the slope stays the same. The slope is still h here, but then this work function is different. And so the work function changes based on the material. And then the easier it is for an for a, like for the compound or element to ionize, or the easier it is for the electron to get ejected. So if you have like a pure substance, the easier it is for the element to ionize, then the lower the work function is. And so for yeah, so like for some metals such as like lithium, which has one valence electron, it requires a low ionization energy, which means that the work function is low. But then for materials which have like magnesium or something with two electrons, it has a higher ionization energy, so the work function is going to be greater. Now, um, so as a recap, the maximum kinetic energy of the photoelectron is equal to the energy of the photon, the instant photon, which is given by HF. So this is the energy of the instant photon, and it's really the energy for any photon is given by HF. And then also remember that F or F is equal to C over V, or C over lambda, which is the wavelength, and C is the speed of light. And so you can also write E is equal to hc over lambda. But this is the energy. So the maximum kinetic energy of the photoelectron is equal to the energy of the instant photon minus the work function. And then remember that light is quantized into discrete packets of energy called photons, meaning that increasing the intensity increases the energy of the photons, of the individual photons, but it doesn't increase the number of photons, and so it can't increase the number of electrons ejected. And increasing the intensity increases the number of photons and the number of electrons ejected, but it doesn't increase the energy of a single photon. All right, thank you for watching.